Good afternoon. Welcome to the fifth in a series of webinars provided by Enable Training and Consulting and our friends at National Instruments. This series is intended for FTC competitors who are here to learn LabVIEW to use with their robot competition this year. My name is Ben Zimmer from Enable Training and Consulting, and I'm here with Greg Sullivan again. Hi. And welcome. In this webinar, we're going to go into a little bit more detail of some of the more advanced features to be used when programming in LabVIEW and how to use them in our autonomous code. To begin with, let's start with a very short review of what we covered last week in webinar number 4. In that webinar, we went into a lot more detail about how to create and modify both teleop and autonomous code, as well as a little bit of detail as to how to test and run our teleop code. We reviewed how to generate teleop code. We can use the remote control editor within LabVIEW to automatically create our teleop code as a starting point. We saw how it's important to set up all the desired hardware settings in the remote control editor, and then simply clicking Generate Code will create our teleop VI. We also learned how to modify that teleop code to customize it. This will allow us to have much deeper control into assigning actions to the controller, and you'll also no longer be limited to the remote control editor's predefined actions. We also saw how the remote control editor can be used to test and deploy the teleop code once it's been generated, or even if it's been modified. This allows us to run and test code without the FCS software. Finally, we reviewed how creating autonomous code in general is a harder task than creating teleop code because it's not automatically generated. We saw how using code created in the Tetrix Getting Started guide is a great idea to get started as something to build upon. The example we created last week was a relatively simple autonomous behavior that combined the operation of reading from various sensors, changing the motor behavior and speed, and also actuating different servos to different angles at different times. This is the flowchart it followed, where essentially if a target was found, it would perform various actions including lowering the arm, closing the gripper, and then raising the arm, and then do a sanity check to make sure the touch sensor was pressed. Whereas if a target was not found, the robot would drive straight and have a varying speed depending on the distance of an object, if detected at all. This is a great starting point and an example of the kind of code that one can use in our autonomous modes. Before we go into detail about the webinar number 5, I want to just quickly remind you of some web resources that are available and a great way to get started. Plus, it's a great way to find the offline versions and recordings of these webinars. From any web browser, go to tetrixrobotics.com/FTC, and what you'll find is a website that will look like this, that takes us through linearly the start in the Tetrix Getting Started guide, through to the FTC extensions, and then ultimately into the Tetrix Mastery material. The webinars that we've been going through, the webinar series, covers all three of these pieces. And webinar 5, which we're in right now, is covering the material that's in the Tetrix Mastery with LabVIEW. This material will be up very soon, so check back often. In this webinar, we're going to cover a topic called step forward or step back. And in a nutshell, it requires using a slightly more advanced programming concept which allows us to remember something from before in order to make a logical decision. The topics we're going to cover are shift registers, a Boolean function called the not function, another function called the select function, and then we're going to create some solution code and explaining it to solve this step forward, step back problem. We've previously seen how both while loops and for loops can be used in LabVIEW to create code that runs over and over again. Shift registers are a feature that can be added to loops that allow us to shift data from one iteration to another. The shift registers can store any type of data, and in fact their color changes to match the type of data stored. They look kind of like this, where inside our while loop we have a triangle terminal on the left side and a triangle terminal on the right side. The two of these are paired together, and essentially a previous value comes out the left side and the current value is wired into the right side. Before we get into the details of using that in the context of a robot program, let's take a quick look at it just using the development environment within LabVIEW. So I'm going to switch into LabVIEW now. From our Robot Project Center, I'm going to create a new VI, which is just temporary, that we're going to delete afterwards. And we're going to make sure that's targeted for the computer, not for the NXT. Just remember, we're just going to show how to use this function. I'm going to create a name for it, Shift Register Demo. And again, to start with, we need a loop. The only way we can remember something using a shift register is to ensure that our code has a loop in it. So we're going to go to the Programming Palette, Structures, and create a while loop. Now remember that the behavior of a while loop is that it will run until a condition is either true or false, and each time through the loop, the value coming out of the I terminal tells how many times it's run previously. So I'm going to create an indicator on this loop iteration terminal. That numeric is, I'm going to call it I, and I'm going to wire in by creating a constant, a false, to make sure our loop runs forever. Now remember, we're not targeting the NXT. We can see that for sure because in the bottom left corner of the screen, we see main application instance. Because that's the case, we have some debugging features that are not normally available when we're targeting to the NXT. The most important of these is called highlight execution, and it's a great way to test out and observe the behavior of the code. So I'm going to turn highlight execution on, and I'm going to just reposition my windows so that I can see both the front panel, and I'm going to scroll so that I can see the indicator that I created on the I terminal. And when I run with execution highlighting turned on, we can observe that the value coming out is first 0, then 1, then 2, then 3. So this isn't a surprise. This is not new behavior, and we haven't implemented the shift register yet. So I'm going to stop this code. Now I'm going to right-click on the edge of my while loop, which will bring up a context window with all kinds of options. But the one we're going to focus on for now is Add Shift Register. Notice when we do that, it added those two terminals, one on the left side and one on the right side. If I click on either one of them, notice that the opposite one is selected. So they're married together. And I can use the positioning tool to move them around, and they'll move together. So there's two important things to remember about shift registers. The first is we need to initialize them. In most cases, it's an advanced topic that we may get into later on in the webinars. There are opportunities when you do not want to initialize a shift register. But for now, let's keep it simple and make sure that we do. So I'm going to initialize my shift register by wiring a value into the left side terminal. I'm going to create a constant. I'm going to do that off of my I wire. Create constant. And just pull that outside and wire it into the shift register. Now, why do we need to initialize? If you think of the purpose of a shift register, it's to remember something from the previous iteration. But before a loop has run, what is the value from the previous iteration? Well, there hasn't been a previous iteration. And that's why initialization is important, to make sure that your code behaves predictably. What I'm going to do now is I'm going to actually wire in the value from my iteration terminal. And I'm going to create an indicator here on my left side terminal and call this my previous I. Just to line these guys up. And again, let's watch the code run with the execution highlighting turned on. First time through, we're going to see 0 in the previous. And then as the loops continue to iterate, we see that our previous I is always following our I by 1. This is a great and very simple way to demonstrate the way shift registers behave. There's also another feature of shift registers. If we actually click on the very bottom middle of the left side terminal, we can expand this guy to show more than 1. What this means is that it's actually going to allow us, and if I create a second indicator, and I'll call this the one before that, just clean up our diagram so it's a little easier to see what's going on here. We need to initialize that terminal as well. So whenever we initialize one, we have to initialize all of them. And let's watch this code run. Well, it's probably not going to be a big surprise. They both start off at 0. And then as we're shifting through the values, we can see that we've got the previous value and the one before that. So this is a great way to remember just the past few values. So I'm going to stop this code. Go ahead and close it. We can save it, but it's not important for what we need to do. And let's return back into our PowerPoint and carry on to talk about some other concepts before we solve the real problem in the context of the robot. The next function we need is a not function. This is not, no pun intended, this is not a surprisingly behaving function. If the input is a certain value, it will flip it. So in the context of Boolean values, if the input is false, the result will be true. If the input is true, the result will be false. And if you think ahead to how we might use this in the context of our problem, remember what we want to do is we want to change direction every time something happens. So maybe one way to do that is to store the direction as a Boolean and use this function to change its value. The next function we're going to need is the select function. Basically, the way the select function behaves, and it looks like this. It's a triangle with an upper and a lower terminal and a Boolean terminal. And basically what it does, it returns the value wired to the T input or the F input, depending on the value of the S input. In other words, it's a select. It selects the true value or the false value. So if you picture this almost like an electrical circuit, it's a Boolean switch that's going to allow either this wire to connect or this wire to connect. And we'll see how this can save space. We've already seen a structure that would allow us to achieve the same behavior, and it's called the case structure. The benefit of the select function over the case structure is when you only have one value to choose between, two values but one signal wire, then it allows you to save a lot of space and not have to wire up a case structure and put the T or the F values through the case structure.